time for you. There's so much that we need to share, so take some time and show you care. Hello everybody, welcome to this week's edition of video notes for Mr. Flugum's AP Chem class. That's right, this is for AP Chemistry, and we are talking about resonance structures, making sure we've got enough electrons to go around. So let's go ahead and get started. So resonance structures are this, right? For many molecules, lots of them in fact, double and triple bonds can be located in different places and sometimes at different times. So what this means is there might be two or more different Lewis dot structures that are equally valid. They might have the same amount of formal charge and things like that, so there isn't any big difference between them. So how does that work? That's what we're going to talk about today. Okay, so one example of a resonance structure is this, ozone. Okay, that's O3 right here. Okay, so what you look at here is you have a double bond and a single bond, right? But we know this about oxygen, it generally likes to form two bonds, right? Same thing here, single bond, double bond. So you can see they're basically kind of mirror images of each other. Now, you might have learned this, and we've talked about this, right? Double bonds tend to be shorter than single bonds, right? Well, in this case, the bonds are the same length because they really each contain approximately 3 electrons. So ozone's real structure is like the average of these two right here. Okay, so effectively there's about a bond and a half between each oxygen atom. Okay, because you only have 3 electrons instead of 4 there. So here's another example of a resonance structure, the polyatomic ion nitrate. As you can see here, the double bond can be with any of the oxygens. Okay, so effectively the number of bonds is this, right? You've got 4 bonds and 3 different atoms, right? Because you've got a double bond and 2 single bonds. Okay, so that means there's about 1 1/3 bonds between each oxygen and the central nitrogen. And if you're wondering, well then what's the real structure of nitrate? Well, it's a combination or an average of all 3 of these. Alright, one more example of a resonance structure, right? So here it is right here, formate. You could either have that there or that double bond there. And remember, those bonds are the same length because they kind of alternate or work back and forth because they're really about 1 1/2 bonds, just like in ozone, right? Okay, so what's the big deal, Mr. Flugum? What do we need to know about this? Well, here's a couple things you need to know, right? About bond length and bond energy. So which structure has the shortest bonds? Well, here we have nitrite, right, which is NO2. And if we look, we have 3 bonds, right, for 2 atoms. So, in the end, that means we have approximately 1.5 bonds per atom. Now if we look at the nitrate down here, right, here we have 4 bonds. If you wonder how I'm getting it like this. 1, 2, 3, 4, right? 4 bonds for 3 atoms. If we do the math there, that only comes out to approximately 1.33. So which one's going to have the shortest bonds? The answer is going to be this one, nitrite, right? That one's going to be the shortest because it has more bonds per atom, right? And remember, a double bond is shorter than a single bond, right? What does this mean about bond energy? Remember, bond energy is the amount of energy it takes to break those bonds, right? So this one right here, since it has the shortest bond length, it's going to have the highest bond energy. That means it's going to take more to break those atoms apart, right? Now nitrate down here at the bottom would have longer bonds, and a lower bond energy. So in some cases, resonance structures are really important because they help us refine and make better predictions about bond length and bond energy and the effective number of bonds. And that can also tell us a lot about how a molecule forms, how much energy it takes to form that molecule, as well as how much energy it takes to break down that molecule. So that's why Lewis structures are useful and important. Well, thanks for tuning in, folks, and I hope you have a great day. I'll see you in class.